In this video, I'm going to present my work titled 2D Local Hamiltonian with Area Loss is QMA-complete. I am Yishen Huang. I'm presently a postdoc at the Center for Theoretical Physics at MIT. My background is in quantum information and condensed matter physics. In this talk, we will consider classical simulation of quantum many-body systems, and I will try to give a relatively comprehensive introduction and the background of this work. In particular, I will introduce local Hamiltonians, quantum Malin author, which is a complexity class that is a quantum analog of NP. And we will discuss classical simulation of quantum states, classical representation of quantum states, and the notion of error law for entanglement. The main result of the work is that the 2D local Hamiltonian problem with the constraint that the ground state-based error loss for entanglement is QMA-complete. This has an implication, that is, if we consider ground states of 2D local Hamiltonians, if we assume that MA is not equal to QMA, then error laws do not imply efficient tensor network representations that support efficient computation of local expectation values. Note that the situation in 1D is different. In 1D, an error law implies efficient matrix product state representations. Therefore, the conceptual contribution of this work is to clarify that the relationship between error law for entanglement and efficient classical representations that support efficient computation of local expectation values. These two concepts, the relationship in 2D is different from that in 1D. Let me start by introducing some basic concepts. We will consider quantum many-body systems. This is just a system of many spins or many qubits. This is a system that is familiar to you because in quantum computing, we just encounter this type of system. When we talk about local Hamiltonian, we assume that each term in the Hamiltonian acts on a constant number of spins. We also consider geometrically local Hamiltonian. When we talk about geometric locality, we first need a lattice. And then spins must be arranged on a lattice so that we have a distance metric. For instance, we could consider spin chain in 1D and 2D square lattice or 3D cubic lattice. And if a local Hamiltonian is geometrically local, then each term acts on a constant number of spins that are close to each other. For instance, we could consider nearest neighbor interaction on a square lattice in 2D. The ground state is just the eigenstate of the Hamiltonian with the smallest eigenvalue. We need to introduce three different types of complexity classes: NP, MA, and QMA. A decision problem is in NP if verifying the solution in the yes instance is in P. That is, a decision problem is either yes or no, and if either yes instance, we must have a classical proof such that the verifier can verify it is a yes instance from that proof. The verification process must be in P. And if we allow the verification process to be in BPP, then we get the class called MA. So MA is a probabilistic generalization of NP. And if the verification process is in BQP, that is, we allow a quantum computer to verify, then we get a complexity class called QMA. So QMA is a quantum analog of MA. Note that for NP and MA, the proof must be classical because the verifier is classical. But in QMA, the proof can be a quantum state because the verifier has a quantum computer. Now let me review the complexity of local Hamiltonian problem. So the local Hamiltonian problem defined as follows. We would like to compute the physical property, and in particular, the ground state energy of the local Hamiltonian. So this problem is in QMA. This is relatively trivial because we first rephrase this problem as a yes or no problem, as a decision problem, so that we have a particular real number, a threshold, and we ask whether the energy is below or above the threshold. It is in QMA because we could give the quantum state to the verifier, and the verifier can just compute the energy. And this process is in BQP, so that the local Hamiltonian problem is in QMA. What is highly non-trivial is that this problem is complete for QMA. This is first proved by Kitaev, which shows who shows that the 5 local Hamiltonian problem is QMA complete. Here 5 means that each term acts on at most 5 spins. But later there are many improvements to this result. In particular, we know that even in 1D with nearest neighbor interactions, such as geometric local Hamiltonian is QMA complete. And even if, in addition, we have translation invariance, then the problem is still difficult in a sense that it is QMA-EXP complete. So here we use QMA-EXP because of technical reasons. You might just very loosely speaking view it as similar to QMA complete. When we try to simulate a quantum many-body system with a classical computer, we need to represent quantum states on a classical computer. But in general, it is not possible to do it efficiently because in a quantum many-body system, the Hilbert space dimension just grows exponentially with the system size, so that a generic state requires an exponential number of independent parameters to describe, so that it cannot be represented in polynomial space. However, we should say that a large class of physical states are highly non-generic, so that one might expect that there might be some clever way to do classical simulation for such class, for some of them, to do efficient classical simulation. So let me ask a trivial question first. What class of our ground states have efficient classical representation? And the answer is that all ground states of local Hamiltonians. This is because in order to represent the ground state, we only need to represent the Hamiltonian. So the Hamiltonian itself can be represented in polynomial space because a local Hamiltonian consists of a polynomial number of terms. And this is because each term acts on a constant number of spins, and all combination of a constant number of spins is a polynomial in the total number of spins. And this representation of just representing the local Hamiltonian, of course, it is a mathematical representation for the ground state and it is in polynomial space, but it doesn't really tell us anything. And we are hoping that we could have a more useful representation in the sense that one can extract physical properties from the representation. So let me modify this question. Previously, we know that all ground states of local Hamiltonian have efficient classical representation. Now, do all ground states have efficient classical representation that support efficient computation of local expectation values? Here, the first efficient means that the representation is in polynomial space, and the second efficient means that extracting physical properties from the representation is in polynomial time. The answer is no, unless MA is equal to QMA. Why? Because if we have such a representation which is itself efficient and supports efficient computation of local expectation values, we could just use this representation as a proof to verify in the definition of MA. That is a classical verifier, but the representation itself supports efficient computation of local expectation values, so that the verifier can just verify it by computing the energy. which puts the problem in MA. However, we know that the local Hamiltonian problem is QMA complete. It implies MA is QMA. If you believe that QMA is not equal to QMA, MA is not equal to QMA, then not all ground states of local Hamiltonians have efficient classical representations that support efficient computation of local expectation values. Then the next question is that what class of ground states have such good representations? It turns out that at least in one dimension, this is related to the amount of entanglement in the state. Let me introduce the notion of error law, which is a notion of low entanglement. Suppose that we have a system and we divide the system into two subsystems, L and L bar. Then we ask the entanglement between these two subsystems. And if the entanglement is scales as the size of the boundary, then we have an error law. If the entanglement scales as a number of sides in L, then we have a volume law. For instance, for a random state, we have a volume law. But for many physical states, we have error law. So in this sense, many physical states have low entanglement. The error laws are of great interest in quantum information, condensed matter, and high energy physics. In 1D, we know that an error law for entanglement implies efficient MPS matrix product state representations. Since computing local expectation values for matrix product states is in P, the 1D local Hamiltonian problem with the constraint that the ground state base error law is in NP. This is because we can just use the MPS representation as a proof to convince the verifier in the definition of NP that it is a yes instance. In this sense, we make a connection between error law and the efficient MPS representation. And also, error law reduces the complexity of the local Hamiltonian problem from QMA to NP. Recall that in general, the 1D local Hamiltonian problem is QMA complete, as has been mentioned before. Now, what is the situation in 2D and the higher dimensions? Such systems are more physically interesting because many physical phenomena just doesn't occur in 1D. And many physicists have tried to generalize MPS to higher dimensions, and such generalizations are called tensor network states. And in the community, it commonly believed that physical states with error laws have efficient tensor network representations. This belief comes from two sources. The first is that it is correct in 1D. And the second is that for tensor network states, many of them are constructed to obey error law. So one might expect that error law states could be represented efficiently by tensor network states. Here, I should say that this belief is not yet mathematically precise because we have not defined what it means by physical. We are not trying to define it, but rely on intuition to judge which is more physical or which is more natural. For instance, ground states of local Hamiltonians are more physical and are more natural than generic quantum many-body systems. Regarding the relationship between error laws and the efficient classical representations in 2D, there are some existing results which says that there exist states which are not necessarily ground states of local Hamiltonians. These states obey error laws but do not have efficient classical representations. Here, I should emphasize that efficient classical representation just means polynomial space, but doesn't say anything about whether local expectation values can be computed in polynomial time. So the proof of this result comes from the idea of estimating how large is a set of all error law states. Indeed, it can be shown that the set of all error law states is parameterized by an exponential number of independent parameters. This just means that the set is too large, so that you cannot expect that you have an efficient representation. That is, you cannot expect that to represent all error law states using a polynomial number of bits. Therefore, generic error law state cannot be approximately represented in polynomial space, and it can not be an eigenstate of a local Hamiltonian, nor a ground state of a local Hamiltonian. Then, what if we restrict ourselves to ground states of local Hamiltonians? This class of states are more physical than the generic quantum many-body states. Furthermore, it is the size of this class is not that large. Because we know that previously, as I have already mentioned, ground states of local Hamiltonians can be represented using a polynomial number of bits. So that the counting approach that is estimating the size doesn't work in this context. The main result of this work is to show that the 2D local Hamiltonian problem with the constraint that the ground state-based error loss is QMA-complete. Furthermore, we could extend this result to the translation invariant case, in which case we can prove that error loss, even if there are error loss, the problem is still difficult in the sense that it's a QMA-EXP complete. We could also extend the result to more physical models, including the 3D Heisenberg and Haber model with local magnetic fields. Even if we have an error law, then the problem is still QMA complete. The implication is that if we assume MA is not equal to QMA, then not all ground states of 2D local Hamiltonians with error loss have efficient classical representations that support efficient computation of local expectation values. Finally, let me give a summary of this talk. First, I have presented an observation which says that if the ground state has an efficient classical representation that supports efficient computation of local expectation values, then the local Hamiltonian problem is in MA. This is because such a classical representation can be used as a proof sent to the verifier in the definition of MA, and the verifier can just verify whether the energy is below or above a threshold from the representation. The technical result of this work is that we prove the 2D local Hamiltonian problem with the constraint that the ground state-based error loss is QMA complete. And the implication is that if we consider ground states of 2D local Hamiltonians, if we assume that MA is not equal to QMA, then error loss do not imply efficient tensor network representations that support efficient computation of local expectation values. This is in contrast to the situation in 1D. In 1D, we know that an error law implies efficient matrix product state representations. And furthermore, error law reduces the complexity of the local Hamiltonian problem from QMA to MP. However, in 2D, the situation is different in the sense that an error law doesn't reduce the complexity of the local Hamiltonian problem. In conclusion, the conceptual contribution of this work is to show that the relationship between error law and the classical representations is different in 2D compared to that in 1D.